Imagine a piece of digital information moving down an assembly line, ready to be sent across your network. Suddenly, it hits a wall. The entire process stops cold. A critical piece of routing information is missing, and without it, no data can move forward. This diagram of a network frame shows how the IP address segment is already filled with data. That IP provides the logical intent. It tells the system who we want to talk to. But to build the physical frame, the computer strictly requires a physical MAC address. Without it, it cannot finish building the frame. The system registers an error, and the packet locks down completely. Having an IP address without a MAC address is like writing a letter to a friend, but having no idea what house they live in. Logical intent means nothing without physical directions. The data is entirely stuck until we find that missing variable. To understand why finding that physical address is so difficult, you have to picture the local network switch as a pitch-black room. The devices connected to it don't come with an inherent pre-built map of each other's physical locations. They're operating in the dark. This creates an immediate problem for the sending machine. It knows the exact identity, the IP address, but absolutely no idea where that machine actually sits on the hardware level. So, how does a machine efficiently filter through a completely blind network to pinpoint the exact physical location of a single specific device? It uses an automated troubleshooting algorithm designed to escape this exact blind spot. It relies on the Address Resolution Protocol, or ARP. The protocol works in 3 distinct steps. Step 1 starts entirely internally. Before shouting into the void of the network, the computer checks its own short-term memory, an internal list known as the ARP Cache. This cache acts as a temporary digital ledger. It stores recent IP pairings and their physical MAC addresses. If they communicated recently, the address is waiting right there. This prevents a redundant network search. But in this case, the internal check comes up empty. The target IP address isn't in the ledger. The sender has no prior memory of communicating with this specific machine. When this internal verification fails, the system is forced to look outside itself. It escalates the search to the external environment, triggering Step 2. Now comes Step 2, the ARP request. Since the sender doesn't know who holds the target IP, it has to transmit a massive signal across the entire local network all at once. This vector map illustrates a broadcast. The central node shouts a digital sonar pulse to every connected device asking, who has this IP address? As the wave hits, receiving devices must compare the requested IP against their own assigned IP. If a receiving computer sees that the numbers don't match, it takes a very specific action. It silently drops the packet. It doesn't send a rejection letter or an error code. It just ignores the request. The broadcast relies entirely on this rule of silent rejection. By quietly filtering out irrelevant hardware, the network efficiently isolates the correct machine without causing any massive system-wide traffic gridlock. And that brings us to Step 3. Out of all the devices on the network, one specific target machine registers a perfect match between the broadcast request and its own IP address. The target device generates an ARP reply. It embeds its physical MAC address into a new message and fires it directly back to the sender. This Unicast is a highly efficient one-to-one line of communication. The missing MAC address successfully locks into place. The Unicast completes the communication loop. Through this specific call and response, an unknown network entity is verified as a physical hardware target. Now we can return to that halted assembly track from the beginning. The system finally possesses the missing variable. The newly acquired MAC address is inserted into the waiting data frame. The error state clears, and the packet construction is complete. The system unfreezes. With the physical routing directions firmly attached, the fully assembled packet launches across the wire, rocketing toward its destination. ARP operates as the core translator of modern networking. It acts as the essential bridge between the logical intent of software and the strict physical reality of hardware. It is an invisible 3-step protocol running relentlessly in the background, millions of times a second. Without it, the entirety of local network communication would simply stall, waiting forever for a physical address it could never find.